This video will narrate my progress on my PhD in the spring 2022 semester. I'm recording this video a little under the weather, so I'm sorry about any sniffles or low energy with narrating the video in advance. So in the spring 2022 semester, I've had 3 papers published in the FLAIRS AAAI conference. They're currently, the camera-ready version has been submitted, and so it's just a matter of time for presenting it in the week of May 15th to May 18th, and then the papers will be published. So the first of the 3 papers was Consistency Learning with Augmented Data, and this is the paper that, I'm super excited about this, and I think this is a great foundation for future work on the things that I think are the most important issues in deep learning, which is what I'll, get into later in the video. The high-level idea of this is that instead of just having our supervised learning loss functions at the output layer, where we compared the final predictions with one-hot encoded class labels such as ship or truck and things like this, we're going to have a supervision at the intermediate representation layer. So typically what we do is we have these images and we put them through these, these say convolutional backbones, things like EfficientNet B7 or say Vision Transformer if it's an attention backbone. And then we say put it through these dense multi-layer perceptron layers, which turn it into vector representations. And then we have our 10-dimensional output vector where we take the argmax to make a prediction on the class label of the image. So what we did in this paper is we moved the loss function. In addition to having the loss function at the output layer, we use the vector similarity of the representations of the original and data augmentation views of the same image to have this consistency at this intermediate representation. And so by moving the loss function back, we can solve this problem of robustness where, and as I'll talk about later in the thing, the robustness is this issue where if you augment an image, it'll make a completely different prediction, even if it's a label preserving data augmentation. So we want to have a, we want it to be representing images that have been augmented with semantically preserving augmentations. We want it to represent these images fairly similarly. So we move the loss function into the representation space. So we explored a few different ways of exactly how to set this up. So the traditional loss function would be a KL divergence between the prediction of the augmented image and then the one-hot encoded class label vector y. So y hat subscript randog denotes the data augmentations that's been used to transform the original image. So what we do is in addition to having the KL divergence between the prediction of the augmented image and the original class vector, we also have the KL divergence between, say, the original prediction and the augmented image, and we explore, y hat and then y bar is how we're denoting where in the representation we're applying this loss. So y hat means the output layer, y bar means an intermediate layer, and then we explore things like SG, which is stopping the gradient in one of the pathways of the network. So if you stop the gradient, it only has backpropagation in this pathway as you have this Siamese prediction pathways. So here are some of the results. We find an extremely promising result by doing this and increasing our our test generalization. But more interestingly is this new metric that we propose in the paper, which is called distributional distance. So distributional distance is about measuring, you first vectorize all the data by putting it through the forward pass of the networks, then you have these output vectors. And so we vectorize the original data set, then we apply data augmentation and vectorize the augmented data set, and then we have the vector, we sum up, take the averages of the vector distances between the 2 data sets, original and augmented. And we want to, the goal is to reduce that distance. So it's not representing images that have been augmented with label preserving transformations much differently. And we find that this works successfully and it increases our robustness, especially random augment tests. This particular jump from 80.6% to 83.1% and simultaneously being able to fit the training set better. We think this loss function is the key to helping with this problem of robustness and having similar representations for label preserving augmentations. So in this paper, what I learned to do also with respect to my PhD and training to become a scientist and make these kind of discoveries is really trying to explore this idea of ablating different characteristics of the experiments. So what we're seeing here is an exploration of the value of alpha to use when we're weighting these two loss functions. So we have the loss function between our predictions and our one-hot encoded labels, and then our predictions of the similarity, whether it's at the logit level with an augmented view or the vector level. And so we explore these different values of that alpha parameter and how they impact the performance. Similarly, we explore the vector level, and we get a really encouraging result with that compared to the logit level. And we think that we can go deeper into the vector level, have multiple loss functions, multiple ways of trading off the loss functions, and projecting that intermediate space to have this loss function. So then, so we do this in a multitask way where we have these two loss functions that are always applied at the same time for every forward pass of two images. We compare this with multi-stage, where you might do one loss function and then the second one sequentially, but we find that doing it at the same time performs the best. And then we explore this problem of stopped gradients, where we stop the gradients because maybe that makes it more stable, but we don't find that perform better. So we plan on continuing this work. We're doing an exhaustive survey on robustness in deep learning, and robustness in deep learning generally refers to this idea where it might predict the original data set correctly as ships, but when you say, this is a pretty extreme case where you've horizontally flipped it and you've also played around with the color quite a bit. But when you do simple augmentations like rotations or cropping, it produces much different predictions and the performance degrades heavily. So we're aggregating all the evidence of this in the literature. So there's all sorts of cases in images and text particularly is what we're looking at. But there's a lot of cases where label preserving augmentations are really destroying these models. So the next paper that I published in the spring 2022 semester was predicting the severity of COVID-19 respiratory illness. And I've shown this slide to show all the authors. And we've been having bi-weekly meetings on Tuesdays. And we've been, a big team coming together to understand this data set from the Memorial Healthcare System and see what kind of predictive tasks we can do with it. So in this video, in this paper, we're predicting the initial severity of a respiratory illness. So this is a categorical scale that we've mapped from the original data set where these represent different kinds of respiratory illness severities and then how frequently they appear in the data set. So the purpose of our data set was to explore this problem of class imbalance. We see that this particular respiratory illness, that's been arbitrarily mapped to 3 in our encoding scheme is 1824 and 52230. So the model is going to be biased to predicting these two classes. And so as we deploy our original models for predicting this, we see that our deep learning method doesn't really outperform the decision tree. But what we're showing in this paper is that something that deep learning lets us do differently from these other algorithms is we can really pry apart the optimization loop. And particularly in this case, we're looking at how we can use random oversampling to play with the data sampling and and solve this imbalance problem. So this is the original confusion matrix. If you just fit an MLP model on this data, you see the number of 4s. It's only got 58 correctly as 4 out of the 224 because it wants to predict it as 3 because 3 is the majority class, and you see the 152 and you see that class imbalance problem. So the first thing we show is that if you just deterministically double every instance in the randomly oversampling algorithm, you get actually a really poor result. But if you have the stochastic sampling, you get a very strong result. And so in the end, we show that this stochastic sampling is a big part of what makes this particular data sampling algorithm work for solving class imbalance. And overall 74.9%, higher than the 73.9% from the decision tree. So by doing this extension to the optimization loop, we're able to improve the performance of the model. So finally, the next paper that I worked on this semester was a comparison of house price classification with structured and unstructured text data. And so the key thing that I was very curious about exploring is this difference between predictions from unstructured data, like text descriptions of houses, compared to symbolic tabular descriptions of houses, and how well you can predict from that with either a deep learning MLP model or, say, a more traditional logistic regression. And so we found pretty encouraging results using the TF-IDF unstructured representation, and then we found actually better results using logistic regression, because we think we still have, we didn't collect a massive data set. So that's probably a key limitation of how far we've made it with this work so far. And we explored more regularization for this. We noticed that, we get 100% training accuracy with the MLP on the TF-IDF. So we added a stronger dropout regularization to try to increase that further. And we did see an encouraging boost in performance by adding this dropout where you randomly zero out intermediate activations of the neural network. So we believe that if we explore more regularization techniques, this could be a really promising kind of idea. So some of the summer 2022 semester plans I have is firstly very interested in this robustness in deep learning. To me, this is such an interesting problem. I can't believe that these models just fall apart like this when you apply these label preserving transformations to them. And so going through the literature and trying to find all the research papers that surface evidence of this, I think is, and understanding what the outstanding solutions are, I think is really important. And particularly, I'm very curious about how this problem manifests in vision and language models. OpenAI, a famous company, has published this model named CLIP, and CLIP is becoming more and more accessible where, even researchers can, like university researchers can access it. So I've been playing around with CLIP, and it's a vision and language embedding space, and we can see how well it can classify images and how robust it is to this same concept of semantically preserving augmentations. With our COVID research group, we plan on extending, right now we had the predict the initial condition based on the, like the demographic information of patients and not too much else. But, we've been having our weekly meetings to really understand the data, understand the treatment plans. And so we can kind of roll this into the time series problem and, have a decision transformer where it's not just a blind time series model, but it is incorporating conscious decisions that are being made to influence patient outcome. So then the final thing is trying to turn these electronic health records to text descriptions. I think this could be an interesting way to represent the data because we have this data set called CORD-19. CORD-19 is a data set put together by the White House, Allen Institute of Artificial Intelligence in Seattle, Georgetown University, several big institutions like this. It's a data set of over 140,000 scientific papers related to COVID-19. And so we'd like to do information retrieval where we take a patient and we turn their electronic health record into a textual description of the patient, and then we use that to get an embedding where we retrieve relevant information from the literature that might help doctors particularly treat this patient. So whether it's clinical trials that there might be some particular paragraph where they make a note, like they might have had some takeaway from their finding where they say patients with this, particular background, such as like age or pre-existing conditions like heart problems or cancer and stuff like that. If we can connect that to the bigger literature and the clinical reviews and all sorts of things like that. So thank you so much for listening to this presentation. I'm sorry, I'm a little sick, so this is probably poorly narrated, but I hope that this was interesting to you to see what I've been up to in the spring 2022 semester.